Good morning, everyone. I'm Wang Bowen, and together with my partner Chen Mohan, we're excited to share our topic: application of linear system in science and engineering. Now, please look at the images on the screens. On the left, we have the brain, representing artificial intelligence. On the right, we have a robotic arm, representing precise physical control. You might wonder what connects biological intelligence and mechanical machines. The answer is the mathematics we learned in class, linear systems. It is the invisible engine behind both. So here is our roadmap for today. We will explore the engine in three parts. First, we will dive into deep learning. We'll see how linear equations allow computers to think and learn. Next, we will move to robot motion control. We'll demonstrate how matrices act as the muscles that move a robot arm. Finally, we will enter the visual world of 3D graphic transformations, understanding how math builds the games and simulations we see. By the end of this talk, you'll see that linear systems are not just formulas on the paper. They are the building blocks of our modern world. Let's get started. When we talk about AI, we often hear buzzwords like neural networks or magic. But as engineering students, we know that there is no magic, only mathematics. If we look under the hood of any modern AI, from facial recognition to ChatGPT, the engine driving it is built entirely on the foundation of linear algebra. In this presentation, I will walk you through how simple linear equations evolve into the massive intelligent system we use today. Let's start with the microscopic view, the neuron. On the screen, you see a diagram of a single neuron. It looks like a biological structure inspired by the human brain, but mathematically, it is simply a linear function. Please focus on the formula. Y equals to f of the sum of wixi plus b. This is the heart of the neuron. X represents our input. For example, if we were predicting house price, X could be the size of the house. W, or the width, represents a coefficient. This is the most important part. If a width is high, the network pays more attention to that input. If it's zero, it ignores it. And B, the bias, is essentially the intercept. It allows the neuron to shift its activation up or down, independent of the input. So, at its core, a neuron isn't thinking, it is just computing a weighted sum. It is a fundamental linear operation wrapped in biological terminology. However, a single neuron can't do much. Modern deep learning uses thousands, sometimes billions of neurons arranged in layers. If we tried to calculate these weighted sums one by one using a for loop, it would be incredibly slow. This is where linear systems save the day. Instead of solving thousands of individual equations, we group them into a single matrix equation. As you can see here, y equals to wx plus b. Here, W is a massive weight matrix that replaces all those individual coefficients. X is a matrix containing a bunch of input data. By converting the problem into a matrix format, we can process huge amount of data in parallel. This is exactly why we use GPUs, graphics processing units, for AI. GPUs are hardware specifically designed to solve these massive linear systems efficiently. Without matrix algebra, modern AI training would take centuries. instead of days. Now a critical question: what does it actually mean to train an AI model? Mathematically, training is equal to solving equations. In your high school math classes, you usually solve for x, but in AI, we already know the input x and the correct answer y. What we don't know is the weight matrix. So training is process of solving for w. However, look at this graph. We have millions of data points, which means millions of equations, but only a limited number of variables. In linear algebra, this is called an overdetermined system. There is no single line that passes through every point perfectly, therefore we cannot find an exact solution. Instead, training is the process of finding the best approximate solution. We use algorithms like gradient descent to adjust the line until the error is minimized. We are essentially fitting a linear equation to the real world. Let's move to a specific application, computer vision. How does a self-driving car see a stop sign? It uses a technique called convolution. While it sounds complex, it relies on a simple linear tool called sliding windows or filters. Look at the green box on the slide. That filter is actually a small matrix of coefficients. As it slides over the image pixels, it performs a local dot product operation. Think of it like a flashlight looking for a specific pattern. If the pixel values match the filter's width, the result is a high number. By repeating this simple linear calculation millions of times, the network can detect edges, curves, and eventually complex objects. Finally, let's talk about the most advanced technology today, large language models like ChatGPT. These models are based on the transformer architecture. The core innovation here is the self-attention machinism, which helps the AI understand the relationship between words. Amazingly, this advanced machinism relies on three parallel linear transformations. When the model processes a word, it projects into three different vectors. Query Q equals to XWQ. What am I looking for? Key equals to W or XWK. What do I contain? Value equals to XWV. What information do I pass on? All three of these are generated by pure matrix multiplication. It is a beautiful example of how basic linear algebra enables the most sophisticated artificial intelligence we have ever seen. To summarize all this, first, linear systems are the skeleton of AI, from the single neuron to the largest model. The structure is defined by linear equations. Second, matrix algebra enables massive parallelism. It allows us to compute millions of parameters instantly by GPUs. And finally, learning is essentially solving for an approximate solution. We are solving over-determined linear systems to make predictions about the world.
Hello everyone, good morning. My name is Chen Luhan, and we have just seen how linear systems act at the brain of artificial intelligence. Now, I will take you on a journey to see how they control the body in robotics and how they build virtual roads in computer graphics. Let's look at the engineering applications. In our engineering journey, we will explore two aspects: robot motion control, and 3D graphic transformations. First, let's look at the robotics. Imagine a robot arm. We know the length of its arms, L1 and L2, and we control the joint angles, which we call theta. But here is a problem. We don't care about the angles directly. We care about where the hand is, that is, the end effector. If I want a robot to reach a specific red dot, how do I calculate the exact angles? This is the brain-hand coordination problem. The relationship between angles and position is actually nonlinear and very complex. However, engineers have a secret weapon called linearization. Look at this equation. Delta x equals j multiplied by delta theta. Here, delta x is a small movement we want, and delta theta is the change in angles. The magic lies in J, the Jacobian matrix. This matrix acts as the robot sensitivity map. It tells us if we change angle 1 slightly, how much does the hand move in x and y. By solving this linear equation, we turn a complex curve into a simple straight line calculation. Let's see this in action. In this demo, the robot is drawing a complex shape. How does it do it? It uses a four-step loop. First, it calculates the gap between where it is and where it wants to be. And then, crucially, it solves the linear system. Delta theta equals the inverse j multiplied by delta x. This inverse Jacobian tells the models exactly how much to turn. And next, it updates the angles. And it repeats this loop every 0.1 seconds. So, smooth motion is actually just solving linear equation thousands of times per second. This math isn't just for lab demos. It powers our world. In industrial automation, in medical robots, and also in autonomous vehicles. They all solve linear systems to interact with the physical world. Now, let's switch gears from the physical world to the virtual world. How do we build 3D games or metaverse? Every 3D object is just a cloud of points. We need to move, rotate, and resize them constantly, like this. To do this efficiently, we use the 4x4 transformation matrix. This is like a Swiss Army knife for graphics. We have matrices for translation, rotation, and scale. By multiplying them together, like this M, we create one single supermatrix that does everything at once. Look at this cube. It is moving right, rotating around three axes and getting bigger, all at the same time. We don't calculate this separately. We simply multiply the cube's coordinates by our matrix M. One calculation, complete transformation. This efficiency is why your video games run at 60 frames or per second. This brings us to our conclusion. Linear algebra is the unified language of engineering. In the physical world, we use the Jacobian matrix to control robots. In the virtual world, we use the transformation matrix to manipulate graphics. Whether we are moving atoms or pixels, linear systems allow us to turn complex problems into computable solutions. And in the end, let's wrap up the entire content. We have seen that linear systems are the skeleton of modern technology. For the brain, they enable deep learning and massive parallel computing. For the body, they allow robots to move precisely and virtual worlds to exist. From ChatGPT to self-driving cars, the underlying math is the same. Linear algebra is not just theory, it is the engine of our future. And that is all the content. Thank you for listening.